Before we dive into that work you've done, I want to properly set the context and also define the problem statement. You've alluded to this thing called quantum mechanics, quantum physics multiple times. I do want to define it. I believe one of the courses you teach at Harvard is Physics 19, Introduction to Theoretical Physics. So I'm hoping this is going to be an easy exercise for you. Let's assume I'm a 12-year-old. Also an easy exercise for you, I'm sure. Not a stretch of imagination. Intellectually, I'm stuck at that age. What is textbook quantum theory? What is quantum mechanics? Please explain it to me as if I'm 12.
Explaining quantum mechanics to a 12-year-old. Interesting question. We look around at the world and we see things. We see people. We see objects. We see phenomena. We see movement. We see behavior. We see patterns. We see patterns all around us. When you see patterns and those patterns are consistent, you see them over and over again, eventually you learn that you can make predictions about things you'll see. You drop an object, the object falls. You drop the object again, it falls in much the same way. You notice there's a pattern. When you observe enough patterns, you start developing ways of talking about those patterns. First, you talk about those patterns in whatever your native language is. But as the patterns get more complicated, we find the need to develop more precise ways of talking about those patterns, of describing them, of telling other people about them, of using those patterns to predict what's going to come next. The precise language that we use for describing those patterns, for explaining, for arguing about, for sharing, for talking about those patterns is called mathematics. Now, mathematics is many things. I don't want to say that the only thing we use mathematics for is for science. But it's one particular thing that mathematics appears to be really good for, and in many ways designed for. We have crafted mathematics, at least in part, to allow us to talk about the patterns in the world that we see around us. When we come up with a nice mathematical way to talk about a pattern, we call that a law of physics. We call it a rule of physics, a rule of the universe. There is a sense in which what we're trying to do in physics is figure out those rules of the universe. Find mathematical expression for the patterns that we seem to see around us all the time.
Okay.
There are debates right now, especially among certain segments in the philosophical community, over what those patterns really are. Are those patterns things that are simply happening for reasons that don't have a deeper explanation, and we introduce this mathematical language just to summarize the patterns that we're seeing, just for convenience? Or is the fact that we see patterns around us telling us that there really are, in some very deep sense, laws that govern the universe, laws that make those patterns come about in a particular way? I don't have an answer to that question, 12-year-old. I don't have an answer. But this is a debate that's raging among philosophers, those who argue that our mathematical laws merely summarize in as best, as optimal a way as possible, have come to be known as the Humeans. This is a term, it's named after David Hume, a philosopher who had a lot to say about the nature of reality centuries ago. The view that the laws of nature are freestanding things just out there in the world that compel phenomena in the universe to behave according to these patterns. That view goes by various names. I like to call it primitivism, the idea that laws are a primitive, basic feature of reality. This is known as the governing paradigm, the idea that the laws exist outside of reality in some sense and act on reality to bring about the phenomena, like governing them, making them behave in a certain way. Now, there's a long-running debate over between the two camps here. The Humeans will say, what does it mean to say that a law of nature exists outside of reality and reaches in? Where does it exist? How does it reach in? How does it make reality obey it? And the primitivists will come back and will say, well, if there aren't laws, are you just saying that these patterns happen for no reason? And if they happen for no reason, then there's no explanation at all. And rather than posit a few laws of physics, you have to posit all the phenomena. That just seems like way more, we call them brute facts, way more things that you're just declaring are out there in the world. And so this debate's been going on a very long time.
Right.
Some of those mathematical rules allow us to say that if we know enough about how things start, then we can predict with certainty where they will go, how they will change, in what way they will end up. Rules of this form, roughly speaking, are called deterministic.
Mm-hmm.
If you're given the starting conditions and you're given these rules, then together, those initial conditions and those dynamical laws, dynamical law means laws that summarize or govern the way things change. Those initial conditions, those dynamical laws determine how things will go, how things will end up. They'll determine them completely. That's determinism. There are other kinds of laws that don't tell us exactly what's going to happen, even if we know as best we can the starting conditions, the initial conditions. What I would say to this 12-year-old is imagine you're playing a game of dice or throwing coins. 12-year-olds mostly know that when you throw a coin, if it's a fair coin, there'll be a 50-50 chance it will land heads or tails. So we would say that if you're trying to describe the coin and its behavior using the language of mathematics, we would not assign a rule that tells us exactly how the coin is going to land. We may not have such a rule, even if we know how the coin started. There is, of course, an argument that if we know exactly how the coin started with incredible precision and we know all the details about how it's thrown, then maybe we could make a deterministic prediction. But in practice, we often don't have that level of description. And so we don't make a prediction about exactly how the coin will land. We'll say the coin has a 50-50 chance of landing this way or that. So some of our scientific theories will maybe involve deterministic kinds of laws, and some of our scientific theories will have laws that talk in terms of probability, chances, probability, the chance that something will happen a certain way or another way. The laws that we got from Isaac Newton, roughly speaking, are of the deterministic kind. If you know that you've got a collection of bodies, of objects in space, and you have details about what condition they're in at the beginning of your experiment, the beginning of your observations, if you have the right kind of information, then you can predict using Newton's dynamical laws of motion, Newton's 3 laws of motion, how this object will evolve or change with time in more or less deterministic way. Now, in practice, this is often not possible. It may be that the behavior of the system depends very, very, very sensitively on those initial conditions, like with a coin, and that we can't make determinative predictions, that we may be stuck using probabilities. Systems in Newtonian mechanics whose behavior depends very, very, very sensitively on the initial conditions, in the sense that tiny changes to the initial conditions that may be too tiny for us to notice can lead to drastic changes in the later behavior. These systems are called chaotic. The study of these systems is called the study of chaos.
Chaos theory.
Chaos theory, right.
Yeah.
So even in the Newtonian case, we may find ourselves having to give up our ability to treat the laws as fully deterministic just as a matter of practice.
Mm-hmm.
And there have been other physical theories since Newton's laws. There's physical theories that describe how electric fields change with time and how they interact with objects, and theories that describe how magnetic fields change with time and how they interact with material objects. And a lot of development has gone into the development of all these theories over the years. In 1900, Max Planck introduced his quantum hypothesis in order to account for certain patterns of observations that were being made about objects that are heated. Heated objects emit light of various colors according to a very particular kind of a pattern. Max Planck was able to account for this pattern, find a mathematical description of it, a precise mathematical description of it, by imagining that you could only trigger or excite different colors in discrete amounts, in steps, not smoothly for these objects. And this became known as his quantum hypothesis.
Mm-hmm.
Over the years that followed, people developed a mathematical theory of microscopic objects, very small things, microscopic theory of molecules and atoms, and eventually subatomic particles, things smaller than atoms, things that you 12-year-old might have heard of, electrons and protons and neutrons that make up atoms. It took a long time to develop this theory. From 1900 to 1925, people relied on a variety of partial mathematical descriptions. This was the era that later became known as the old quantum theory. Formulas that sort of worked but didn't quite work. Formulas that didn't quite fit together into a comprehensive set of equations. That didn't fit together into a mathematical framework that was unified, that fit together like a jigsaw puzzle fits together. I could go deeper into the history. I've gone deeper into the history in other conversations. Let me not do that here. People are welcome to go look up, the history themselves or listen to, the descriptions I've given of the history elsewhere. But let me just say to this 12-year-old, the theory that developed starting in 1925 and reached its culmination in the early 1930s with the work of people like Paul Dirac and John von Neumann, with a tremendous amount of work by others like Wolfgang Pauli and Louis de Broglie and Erwin Schrödinger and Werner Heisenberg. The theory that developed has the following structure. We start with some basic ground rules or assumptions, the starting points, the postulates, the axioms. You can use different words for these things. These are the raw mathematical starting ingredients out of which we're going to build the theory. Much like we build Newton's theory of motion out of his idea that we have material bodies in space, obeying his famous 3 laws of motion. What are these axioms? What are these postulates or premises? The first is that we will not talk about bodies in space. Instead, we will assign a system being some physical thing that we want to study and make predictions about. We call that a system. We will assign it a mathematical thing, and this mathematical thing is called a quantum state. Now, 12-year-old probably doesn't maybe know very much about Hilbert spaces, so I'm going to avoid using that language here. I'm just going to say that we have this mathematical thing called a quantum state.
Right.
It has some basic rules, some basic mathematical properties and rules, but these rules are all purely mathematical. There's statements about how this mathematical thing is supposed to, what mathematical features, what kinds of mathematical operations you can do with it. This mathematical thing, when not disturbed, when left to itself.
Not measured.
Certainly not measured.
Not measured.
Not measured.
Is that what you mean by not disturbed?
Not necessarily. Measurement is one kind of disturbance.
Okay.
There are other kinds of disturbances. If our system, the system that we're trying to describe with this quantum state, is left to do its own thing, it's not interacting with, it's not talking to, it's not exchanging things with any other systems, then it changes according to a rule. And this rule has kind of a funny name. It's called unitary time evolution. This can often be boiled down to a very famous equation that appears on the very first page of David Griffiths' textbook called the Schrödinger equation. So there's an equation that tells us how this thing changes, this mathematical thing changes when the system is not being disturbed. But so far, all the things I've said have been purely about mathematics. We have a mathematical thing called a quantum state, and it changes according to this mathematical rule called unitary time evolution. How do we connect this up to the patterns that we see in nature around us, to our observations? That is, how do we get the empirical content out of this picture? Empirical just means the things that we experimentally observe or see. Those come from some additional assumptions, some additional premises or axioms. These are called the measurement axioms. The measurement axioms say that if an observer, one who observes, like a person, let's say, but maybe not necessarily a person, but maybe not necessarily a person. This is a bit mysterious. But when an observer of some kind measures some property of a system described by some quantum state, there is another kind of mathematical thing. This other kind of mathematical thing is called an operator. And the mathematical features of this operator, when studied, allow you to predict what you could get when you read the results of your measurement. The things you can get are called eigenvalues. They're called the eigenvalues of that operator. The word eigenvalue apparently came from David Hilbert, the great mathematician from the end of the 19th and into the 20th century. He was at Göttingen. So the eigenvalues are a list of features of this mathematical operator. And by studying this mathematical operator and by figuring out what these numbers, these eigenvalues are, they're real numbers, you can predict what are the possible things you could find when you measure that property of the system. That's a prediction about what you'll see in nature. That's a prediction about a pattern. When you measure this property of this kind of system, you'll always see one of these specific numbers, one of these eigenvalues. So we're already connecting with patterns of things we see. There's a pattern. We see certain kinds of things and not other kinds of things. When we measure this feature, this observable property of this kind of a system, that's a pattern. And now we're beginning to see an axiom that tells us about those patterns that we see. The next measurement axiom tells us what are the chances that we'll see one of those numbers, or one of the other numbers, or one of the other numbers. It's an axiom that tells us what the probabilities are going to be of our measurement outcomes. There's a precise mathematical formula that takes the mathematical quantum state from our first axiom and takes the operator from the axiom I just mentioned and combines them together in just the right way. And this formula is called the Born rule. It's named after Max Born, one of the people who developed quantum theory. And we get a prediction for the probability that we'll get that particular outcome. This Born rule axiom lets us make predictions about measurement outcome probabilities. Mm-hmm. It allows us to assign a probability, a number, a different kind of a number, not the number of the thing we're measuring, but a number that tells us what are the chances we'll see that particular number of the thing we measure. Just like with a coin, we can say that for a fair coin, there's a 50-50 chance. The Born rule says that for different properties we could measure, there's certain probabilities that we'll see particular results. The final assumption or axiom that leads to quantum theory says that after you've done your measurement and obtained a particular numerical outcome, one of the eigenvalues, you're supposed to change the system's quantum state in a very particular way. You're supposed to simplify it or reduce it or collapse it in such a way that were you to do the same exact measurement again of the same observable feature, then with essentially perfect 100% chance, you would get exactly the same answer you found in the previous measurement. This is known as the collapse postulate or the collapse axiom. And those are the axioms of quantum theory. Those are the axioms that you'll find when you read deeply enough into any good textbook on quantum theory. That includes David Griffiths' book. These are the agreed upon axioms, and they're known as the Dirac from Paul Dirac, von Neumann from John von Neumann, the Dirac-von Neumann axioms. And this is the part that people mostly agree on. Mostly. At least people agree that if you're talking about textbook quantum mechanics, textbook quantum theory, then these are the axioms you're taking to be your starting mathematical ingredients. I should say that I sometimes say quantum theory and sometimes quantum mechanics. Sometimes people use the word quantum theory to mean the general theory, quantum of anything, and quantum mechanics specifically when quantum theory is applied to systems of particles in particular. But there do appear to be other kinds of things in the world like fields, like the electric field, the magnetic field, the gravitational field, or systems in computers made of memory registers, bits inside of a computer memory. Maybe those are ultimately made of particles, but when we describe them with quantum theory, we're not using the usual quantum mechanics of particles. So some people use the word quantum mechanics specifically when the kind of system we're trying to study is explicitly made of particles. Although sometimes people use the word quantum mechanics more broadly for the overall theory. So those are the axioms. Now here's what I would tell the 12-year-old. Maybe you've watched a science documentary, or maybe you've been in school and read in one of your books, or maybe you've read a science fiction book, or maybe you've listened on the radio to a program where people were talking about quantum theory. And maybe you've heard them say things like, quantum theory tells us that an atom can be in two places at once. Quantum theory tells us that when a particle goes from point A to point B, it takes every single path from point A to point B to get there. Maybe you've heard, maybe in a elementary or middle school chemistry class, that an atom is not empty, but it's really filled with a cloud. An electron is kind of a cloud made of what's called a wave function, and this wave function fills the atom. Maybe you've heard that a cat can be alive and dead. Maybe you've heard that quantum theory tells us that everything that can physically happen does happen in some giant branching quantum multiverse. But maybe you've heard even simpler things. Maybe you've heard that electrons can move around and every once in a while they spit out a photon. Or maybe you've heard that when an electron meets an anti-electron, a positron, why is it that electron antiparticles get a name, positron, but others don't? Anti-electrons get a name called positrons, but electrons, funny. But when an electron meets its antiparticle, they can annihilate and become a photon. So you imagine this picture where an electron is moving in one way and a positron's moving another way, and they come together and a photon comes out. But if you look at the axioms that I listed, the Dirac-von Neumann axioms, quantum states, unitary evolution of these quantum states, all pure mathematical, and then these measurement axioms, you could measure something and you get an eigenvalue of a certain kind of mathematical operator with a probability given by the Born rule, and the quantum state is supposed to change, collapse. The axioms say nothing about any of those things. The axioms do not say that a system can be in two places at once. The axioms do not say that systems take every path from point A to point B. The axioms don't say that an atom is filled with wave function. The axioms don't say that a cat is alive and dead or can be alive and dead at the same time. The axioms don't say that every possible physical thing happens in some sprawling, vast quantum multiverse, branching and branching from every point in time. The axioms don't say that electrons can just emit a photon, or that an electron and a positron, they meet, they find each other, they meet, and a photon comes out. The axioms don't say any of that. The axioms talk about these abstract quantum states changing, and then the axioms tell us what happens when we do measurements, and that's it. That's striking, isn't it? And very different from the axiomatic formulations of our other physical theories. Let's go back to Newtonian mechanics again, Newton's picture of the world. There are bodies moving around in space. I didn't say what Newton's laws were, but the laws talk about different frames of motion you can make observations in, and how in those different frames of motion objects will behave. They'll follow straight lines at constant speed unless they interact with each other through forces. And if you know what the forces are, you can predict how the bodies will change in motion, how their motion will change. Yeah. This gives a very physical picture of what's going on in the world around us, and in particular, a picture that doesn't rely on somewhat mysterious ingredients like observers or agents doing mysterious things like measurements. When you look at how we formulate our other physical theories like electricity and magnetism, or Einstein's theory of general relativity, you get much more mathematically complicated theories. But you still get theories that paint pictures of phenomena happening in the world, whether we as observers or agents are there or not, that describe things changing and doing things, following paths, exhibiting behavior. These are theories in which phenomena happen in a very broad sense. There's this category consisting of phenomena taking place, and these theories say that those phenomena, at least at their level of scientific description, really are happening. These are phenomena happening theories. But the axioms of quantum theory don't seem to be like that. They don't talk about phenomena happening. To the extent that they make a connection to reality, to empirical reality, it is only through the very narrow category of measurements, apparently done by observers or agents. This is not satisfying. This is troubling. But that doesn't mean it's wrong. I mean, no one ever promised us a rose garden. Maybe nature just isn't forthcoming with happening of phenomena in what is presumably our most important fundamental scientific theory, quantum theory. Maybe that's just the way things are. However, as an intellectual exercise, I think it's worthwhile to see if we can reformulate quantum theory as a theory of phenomena truly happening. And even more, the fact that people tell these stories about quantum theory, things being in two places at once or following all these paths, or that electrons really are moving around and emitting particles and so forth, the fact that people tell these stories means at some level people really do still think this way. It would be nice for this to be honest. It would be nice to be able to tell someone who's studying early universe cosmology that when they talk about what gases were doing in the early universe, they're not just telling a colorful tale, but they're describing something that really happened, phenomena that really happened, even though there was no one there looking at it as it was happening. It would make us more honest to be able to transcend this narrow category of measurement phenomena alone and be able to talk about this much broader category of phenomena happening. That is, it would be nice if we could transcend this category problem in quantum theory.